Hey everybody. Alright, so today we're going to implement a ring buffer. Beginning of the year I did a theory video around ring buffers, so make sure that you go watch that before looking at this so that you can at least have a grasp of what I'm doing as I walk through. And then, so I figured we did that, so may as well go ahead and do the implementation. So we're going to do this ring buffer, okay? So as usual, I'm going to go through and I'm going to knock out this code from memory, and just to show you how easy it is to kind of just walk through the process and the algorithm, the data structure. And then we'll do a code review. Now I'm going to do this a little bit differently, so posting the notes to different platforms and stuff, it sucks. So what I'm going to do instead is I'm just going to publish the Notion page, and you guys can go look at it. And you'll always have the notes, and I'll post the link down there. Okay? All right. So let's get started. All right. So first things first, we got to see the thing. All right. So this is what let's do our ring buffer itself. Okay. Now there's going to be a number of members. Okay. So head, tail, length, capacity, and we need a buffer to hold the things. Okay. Now let's implement. Okay. Do the constructor. We want to define a capacity, and then to return self. Oh, and we need clone here because of the way the vector macro works, right? So let me show you. All right, so this can be 0, 0, 0. This needs to be capacity here, okay? So the way that the vec macro works, it clones, right? It clones this, your vector, right? So here we're just cloning a bunch of empty vectors. This is really a type compatibility thing. This has really nothing to do with cloning. I'll explain it to you in the code walkthrough. This is a very cheap clone, the cheapest clone you could do. Okay, so don't sweat that. You can implement this without clone if it bugs you, but I find that doing it this way, we can stick to focusing on the data structure and not, worried about Rust syntax things. Okay, so now we need a bunch of little methods to basically so that we can peek at certain things. Okay, so length, right? So a cap, right? So that we can look at the capacity. Okay, we need to be able to tell when the thing is full and when it's empty. Is empty. Now, how do you think we can tell this thing is empty? Should be pretty intuitive. If the length equals nothing, empty, right? Now, how do we tell if it's full? Should be pretty intuitive as well. Self.len equals self.cap, right? If your length equals your capacity, well, you're full. Okay, now, okay, so mental model that you need to think of, right? Don't think of head and tail as buckets that something go in, okay? You need to think of head as pointing to the next value that is going to be removed. We are always going to pop from the head, and we're always going to push to the tail, right? So head, well, what do you need to pop? You need the value. So the value's there, right? So the value is there in head, but that's how you need to think about it. It's not a bucket holding something. It's basically pointing to the next value that's going to be popped. And this mental model will become is important, and that'll become clear. Okay. Now tell, it's pointing to the next value to be pushed. What do you need to push a value? You need an empty slot. So tell is pointing to nothing right now. Now that's important. Okay. That's important to remember. Okay. So here we go. Okay. So this is going to be next. Okay, now okay, so modulo. Okay, this is very important, guys. Like the modulus is used, I would say probably the thing that modulus is used the most for is confining a wraparound. Right, basically defining a wraparound within a set of bounds, right? Like, so when you rotate, like say when you rotate an array, right? So say that you rotate an array once left, okay? So say that you got an array 1, 2, 3, 4, 5. The capacity is 5, and you want to rotate left. Well, you would use a modular arithmetic to ensure that when you rotated that thing around once, it would read 5, 1, 2, 3, 4, right? So so what this is doing is this is progressing forward around the ring. Okay, now this next one, what this is going, and I'm actually going to walk through the arithmetic here and show you how this works and why it works. Okay, now this one here, to get this, you do I plus the capacity minus 1, and then the modulus of the capacity. Okay, and I'll walk through this as well to show you. Okay, now we need a way to be able to peek at the head and tail and basically know what those are pointing to. Okay, so remember that mental model. So we're going to do pub front. Check if it's empty. Now, the front, like I said, head is the next value to be popped. What do you need to pop? You need a value. It's already there, right? Because, well, you're popping head. Okay, so you can, in buffer, you can just go directly to head and you can grab it. Okay, now, what about the tail? So for the tail, right? Just want to make sure I don't call these things the same thing. All right. Yeah. Use size. Okay. We're gonna test if empty again. Okay. Now here. Tail is pointing to the next index that is going to be pushed to. So what do you need to be able to push? You need a blank index, an empty one. So tail is currently blank. It's waiting for a value to be written to it. So what you have to do is go back one. So you have to do this. Inside the buffer, you go back to the previous index, you grab tail, and then you bring it back as a reference. Okay? Okay? Now, let's do our push and pops. Get some things in here. Okay? Now here we're not doing anything special with return. So whatever, we do need T for the error though. Okay, so that's what that return means. Okay, so here we need to check if it's full because we're pushing. All right, and then if it is, I want to return the value that we're trying to push. Okay, so then what we can do is we can go, well, a great example here again of the mental model. So self it's waiting, right? It's waiting to be pushed to. So we can go into the buffer and get it directly. Right? Then what we need to do is we need to advance tell so that it's in the proper position to be pushed to again when we're ready to push to it. All right? And that's what that next method is for. Okay? We add 1 to the length because we pushed to it, and then nothing exciting with the return, so we're just going to do okay. All right? Now, pop. Changing the, I got this generic, a bunch of generic ambient stuff that I've added to my background and didn't want someone talking over me. Yes, the ambient music. I hope you guys like that stuff. I wanted something different in the background than most people play. Most people play like this cheesy like circus stuff and not my vibe. So, but yeah, so I hope you like the ambient stuff. Okay, so pop. So here we're just going to return that. So now we got to check if it's empty, right? Because if there's nothing there, there's nothing to pop. None. Check. All right. Now here. So what do we have to do for head to pop? Okay. So we have to do this. And I will explain that in the code walkthrough. Okay. Take basically grabs a value and puts none there. Does it in one swipe. Okay. That's what it does. Okay. Now we can do the same thing. Get head set up for the next pop, and then we'll reduce the length because we're popping one off, and then we'll just return item. Okay. Now I do have this method down here. This is going to be like a little helper method. And what this does, this has nothing to do with a ring buffer, guys. This is just a little method that I wrote real quick to be able to show you the loop, the way that the ring kind of loops on itself. Okay, that's all that this is going to show. Okay, now let's go over to main. And don't worry about all this. The main thing you need to worry about is that I am filling up the vector. I'm filling up the ring buffer. It has a capacity of 3, filling it with A, B, and C. Okay, so let's run this. Okay, up here, it's complaining that I didn't use that cat method that I defined, so that's whatever. But so let's look here. Okay, so we'll see that the starting state, we have nothing in there, it's empty, and it is not full. Okay, so remember, I pushed, I filled it up, right? So it's full. So after this, it's full. So I try to push D, we get an error back, right? Then we pop A, which reduces us to a 2 length. We have B in the front and C in the back, right? We push D. Since we pop D, we have room for D now. So now our length is 3. Our front is B and our back is D because we add to the back and push the other values forward. And then this shows you the cycling, right? BCD, 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 BCD. The ring buffer, it's confined to a capacity of 3, and those 3 values just loop around, okay? And I'm going to leave, and so I've added these comments for you guys in case you get a little bit confused about what's going on. These comments will be available in the GitHub repo. All right. Okay. So we're successful there. Let's do the walkthrough. Okay. So mental model. Once again, head is the index of the next element to remove. The slot currently holds a value when non-empty. Okay. Tell is the index of the next empty slot to insert to. All right. And then length, of course. And then we're empty. Pretty self-explanatory there. Okay, so here we're defining a ring buffer. We got 5 fields, We got 4 usize, they'll be holding indices, and then we have a buffer field set to hold a vector of options, right? Generic. Okay, so here's the clone bit. Okay, so really this should not be groundbreaking for anyone, right? So the only thing to really point out here is the T clone, right? And so we use this because we create this storage, right? And this macro means make a vector by cloning this value none capacity times, right? So this vector macro needs clone to be able to do its thing. That's the only reason that we're using it, okay? And like I said, this clone is as cheap as it gets. None does not have T. There's no T data, so there's nothing to duplicate. Option, so you know, it's a trivial constant time. We're just constantly returning none, right? And then there's no heap, there's no copying, no allocations. It's super cheap, so don't sweat it, okay? Like I said, it's a capability check, right? Not a cost. I think I may have said type. That's wrong. It's compatibility check. All right. So the first method's attached to the ring buffer. Straightforward, right? We're grabbing the length, we're grabbing the capacity, we're checking if it's empty, we're checking if it's full. Shouldn't be anything out of this world there. Now, this is where it gets a little interesting, okay? So next and previous, okay? So what these methods do is move circularly around the ring buffer by progressing forwards or backwards through the ring buffer, all right? So let's show you how the arithmetic works out, all right? Kind of prove how this works, and within basically how the modulus is confining this wraparound within these bounds. Okay, so let's say our ring buffer contains 1, 3, 5, 7, and 9. Right, now we have a cap of 5. Okay, so I is the index of the current value being passed. In our example, the array 1 element is 3. Right, so this one. Okay, so we do 1 plus 1 because I, right, that's what I is. So it's the position in the array. So 1 plus 1 modulo 5 is 2 modulo 5, 2, which is the next index from 1. Okay, so let's say that we pass in 5, right, the 2 element. So 2, right, I plus 1 is 3. 3 modulo 5 is 3, the next index from 2. Okay, and then we go all the way to the last one, right? The 4 element. 4 plus 1 is 5. 5 modulo 5 is 0. We are back to the first element, right? So this is what gives us the loop going forward. Previous works the same way, okay? So we have our ring buffer with the same values. Here we're adding self.cap and subtracting 1. So let's say we pass in 5, the middle value. The 2 element, right? 2 plus 5 is 7, minus 1 is 6. 6 modulo 5 is 1, the previous index from 2. And then it wraps around backwards, right? So you see that the modular arithmetic here is key to that. And guys, you will see that used all over the place. Like, you know, I'm doing the hacker rank stuff now for you guys. We're walking through that. That technique is all over the place in those questions. Okay. Now, front and back. Okay, so these allow us to peek into the front and back, right? By reference. So this one, like I explained, pretty easy, right? This, you go into the buffer, you grab the head, and you return it as a reference, right? And we're returning has ref, right? So there's a borrow, there's no move. Now, the back method. Now here, we can't just grab we can't just, I need to change that. We can't just grab, well, did I word that right? We can't just grab self.head like we could in front. That's right, we can't do that, right? So this is because the back element, the most recently inserted, lives at tel minus 1, like I keep saying, right, with wraparound, not at tel. That's why we have to do the previous self.tel. All right, so let's walk through that. So let's say that we have a capacity of 3, and then we have everything set to 0. All right, so when we push A, we write at tel 0. That's where we write to. But then remember, in the code, we advance right here, right? We advance. We go forward 1, right? And so we write at 0 and then we advance to 1, right? So at this point, we have something written at A, and our tail is pointing at index, or tail is at index 1, okay? So front will read head 0, which is A, right? This is indexes. This is not amounts, okay? So, right, so we read from head 0, back reads previous tail, which is 0 from 1, and that's A, right? So let's go back, right? It would look at index 1, which is empty, and advance to 2, right? So you notice how tail always points to the next insertion slot, right? So the last valid item is 1 step behind it. That's what you guys need to remember. That's why I keep saying it. The mental model is head is next to pop and tail is next to push, right? Head points to the slot that currently holds the next element to be removed. Tail writes, and it points at the next empty slot we will write to, okay? The terminology, and it can be a little confusing at first until it really sets in, right? So that's why I keep repeating it. And then finally we have push and pop. I mean, these are pretty straightforward, guys. I talked pretty good bit about them. I basically laid it out when we went through the code. I talked about this return value. That's kind of what I talk about here. And then here, you know, we walk through this part, all right? So we write some value to our tail, we advance the tail an index so that it's ready for the next push, increase the length because we've written to it, and then we return the result. Right? Now the only thing about the pop method, it's really take. So we're doing self.buff, self.head, and then we call take, right? So what take does, like I said, right, it returns the current contents and replaces the slot with none in a single go, right? So, and Rust won't let, and so this kind of explains it, right? Rust won't let us just move a value out and leave it uninitialized. It has to have something there. And so that's what take does, right? Take removes the value and puts none there so that it's not uninitialized. It's not empty memory. Right? That's all. That's why we're using take, is to ensure that there's something in that slot when we get the value from it. Right? That's it. Now let's talk about some big O. I mean, as you see, pretty much everything is constant except new. You know, pop is constant time. It doesn't depend on n. It has a single assignment into a vector slot, a simple modular addition, and an increment of a counter. Right? Nothing depends on n. Now, we avoid amortization here because we have a fixed capacity, right? We never reallocate. So once full, push just returns the value, right? It's an error. However, if we did not limit capacity, we would have a truly resizable array on our hands, you know, a vector of, you know, of generics values. Right, so this means push would be amortized because when the underlying storage fills, vec doubles its capacity, right? So, but we don't have to worry about that here because we have a fixed capacity, right? Right, front and back, also constant time, doesn't depend on n. Each action does a single indexing operation and returns a pointer, right? There's no loops, there's no allocations, nothing. All right, so new is linear time because it has to allocate space for n slots and fill them with none, based on the capacity, right? So this is 1 write per slot, which means linear time. It's dependent on that. It's just dependent on n, right? It's dependent on the number of elements, okay? And but remember, this cost happens only once when we create the buffer, not per operation. Right, so very efficient data structure here. All right, guys, that is it. Like I said, I will be posting the Notion link. The code, I believe, is already in GitHub. I will include that in the description. It'll be the same as before. There will be branches where you can see the different data structures, right? That we've done so far. I believe it's just called YouTube lessons, right? Yeah. All right, guys. That's it. Hope you learned something. If you have any questions about this stuff, hit me up. Help each other out in the comments. Ask respectable questions. You'll get respectable answers. And yeah, we'll see you in the next one. All right, guys.